Good morning, students. This is Arvind, Assistant Professor, Department of Physics, D.Tech, Kavali. So, in the previous class, I discussed about some objectives of series compensation. And now, in this class, I am going to discuss the functional requirements of the series compensation and basic approaches of series compensation. And next, I am going to discuss the variable impedance type series compensation methods. Okay. So, firstly, I will discuss the first concept of today's class, that is summary of functional requirements in a series compensation. So actually the series compensator is primarily applied to solve power flow problem. So I already said this one. So the series compensator is primarily applied to solve power flow problem. So these problems may be related to two conditions. One is length of the line or the structure of the transmission network. So here we have the power flow problems. So actually the series compensator is primarily applied to solve the power flow problem. The power flow problems in the series compensation, that in a transmission system, is two ways. One is the length of the line and another one is structure of transmission network. So the electric length of the line can be shortened to meet power transmission requirements by fixed compensation of the line. Okay, the electric length of the line can be shortened to meet power transmission requirements by fixed compensation of the line. And next, coming to the structure of the network. So the network structure related problems which typically result in power flow unbalance. Okay, network structure related problems which typically result in power flow unbalance. So as well as parallel and loop power flows. Okay, as well as parallel and loop power flows. So may require controlled series compensation at the time, and particularly if contingency or planned network changes are anticipated. So at that time we have to introduce this controlled series compensation for the transmission network structure. So okay. So next one. So fixed or controlled series capacitor compensation. Okay, fixed or controlled series capacitor compensation can also be used to minimize the end voltage variation of radial lines and prevent voltage collapse. Okay, fixed or controlled series capacitor compensation can also be used to minimize the end voltage variation of radial lines and prevent voltage collapse. And series compensation appropriately controlled to counteract the prevailing swings can provide significant traction stability improvement for post-fault systems and can be highly effective in power oscillation damping. Okay, so by using the series compensation, it is used to counteract the prevailing machine swings and also to provide the traction stability improvement for post-fault systems, that means after the fault clearing, and can be highly effective in power oscillation damping. So in the previous sections I discussed about this traction stability improvement and power oscillation damping concept in the objectives of series compensation. Okay, by using the series compensation, we have to improve the traction stability and highly effective in power oscillation damping also. And appropriately structured and controlled series compensation can be applied without the danger of subsynchronous resonance to achieve full utilization of transmission line. So this subsynchronous resonance concept also I discussed in the previous class. Okay, so by using the appropriately structured and controlled series compensation can be applied without the danger of subsynchronous resonance to achieve full utilization of transmission lines. Okay, next. So in future, flexible AC transmission systems where various controlled series compensators will play a key part in maintaining power flow over predefined paths. Okay, in future, the facts, that is flexible AC transmission systems, consist of various controlled series capacitors. This will play a key part in maintaining power flow over predefined paths. Power flow over defined paths. So these are establishing alternative flow paths under contingency conditions. and manage line loading and generally ensuring the optimal use of the transmission network. Okay, so and it will be seen that analogously to shunt compensation, control series compensation to meet the above functional requirements can be accomplished by both thyristor controlled impedance type and converter based voltage source type compensators. So in the previous shunt compensations, we discussed about the PCR and TCS concept, TSC concept, the thyristor switcher and thyristor controlled concept by using voltage source type compensators. So in this one also, we are using the functional requirement to meet the above functional requirements can be accomplished by both TCS, the thyristor controlled reactor, thyristor controlled capacitor, TCS, the TSC and TSR concept based on voltage source type compensators. And however, the operating and performance characteristics of the two types of series compensators are considerably different. Okay, however, the operating and performance characteristics of the two types of series compensators are considerably different. Next, so that is the explanation for the summary of functional requirements. So in that one we discussed about the how many functional requirements we have to take for the series compensation compared to the shunt compensation, and what methods we have to take to achieve those functional requirements. We discussed it, and next we are discussing approaches to controllable series compensation. Okay, approaches to controllable series compensation. So actually in the previous chapter, that is the shunt compensation, we discussed two basic approaches. Okay, so that is as described in shunt compensation, there are two basic approaches to modern power transfer shunt compensators. In that one, first one is which employs thyristor switched capacitors, that is TSC, and thyristor controlled reactor, that is TCR, to realize a variable reactive admittance. And the other is which employs a switching power converter to realize a controllable synchronous voltage source. Okay, which employs a switching power converter to realize a controllable synchronous voltage source. These are the two basic approaches we discussed in the shunt compensation concept. And the series the series compensator is a reciprocal of the shunt compensator. Okay, the series compensator is reciprocal of shunt compensator. That means the shunt compensator is functionally a controlled reactive current source. Okay, the shunt compensator is functionally a controlled reactive current source which is connected in parallel with the transmission line to control its voltage. That is the shunt compensator. And in the series compensator, so the series compensator is functionally a controlled voltage source which is connected in series with the transmission line to control its current. Okay, that is the difference between shunt compensator and series compensator. So the series compensator is functionally a controlled voltage source. So the shunt compensator is controlled current source which is connected in series with the transmission line in the series compensator, but in the shunt connected controller, so in that one which is connected in shunt with the transmission line to control its voltage in that one. So here we are controlling the current. Okay, so that is the difference between shunt connected controller and series compensator, and this reciprocity suggests that both the admittance and voltage source of shunt compensators have a corresponding series compensator. Okay, so that means this reciprocity suggests that both the admittance and voltage source of shunt compensators have a corresponding series compensator. So indeed, as indicated earlier, the series compensator can be implemented either as a variable reactive impedance, okay, variable reactive impedance, or as a controlled voltage source in series with the line. Okay, as a controlled voltage source in series with the line, like that we are taking. Okay, next, so because of this duality, so here we have a duality problem. So because of this duality between the shunt and series compensators, many of the concepts and circuit and control approaches discussed in shunt compensation are applicable. So in the shunt compensation we discussed so many concepts and the approaches also. So those approaches and the concepts are applicable to this series compensation also with a complementary view in the present discussion. Okay, with a complementary view in the present discussion. So that is in shunt compensation, the basic reference parameter is the transmission voltage. So in the shunt compensation, we have the reference parameter as the transmission voltage, and in series compensation, it is the line current. Okay, in the shunt compensation, that is the transmission voltage. In the series compensation, the basic reference parameter is the line current. Okay, so therefore, the operation of the shunt compensator is viewed from the perspective of the transmission voltage and that of the series compensator from the perspective of the line current. Okay, so I think you understand this one. What is the difference between shunt compensator and series compensator? And next, so this complementary relationship will be exploited in this concept, that is in the series compensator, to build upon the principles established for shunt compensators in the previous concepts and extend them to series compensation so as to develop a general understanding and unified perspective for the role and the application of controllable reactive compensation for electric power transmission. Okay. So next, coming to the next concept, that is variable impedance step series compensators. So actually in the shunt compensators also we have this concept. So that is variable impedance step shunt compensators, and in this one we have variable impedance step series compensator concept. So this is very important concept. So in this one we have, just as in reactive shunt compensation, that is in the previous chapter. So the variable impedance step series compensators are composed of thyristor switch or controlled capacitors or thyristor controlled reactors with fixed capacitors. So like that we have in the series compensator also, but we have three types of variable impedance step series compensator. We have first one is GCSC, that is GTO thyristor controlled series capacitor. So GTO thyristor controlled series capacitor, that is the first one, and next one is thyristor switched series capacitor, that is known as TSSC, thyristor switched series capacitor, and lastly we have thyristor controlled series capacitor, that is TCSC. So we have three variable impedance step series compensators. So now in this class I am going to discuss the first one, that is GTO thyristor controlled series capacitor. I will discuss in this class, and in the next classes I am going to discuss remaining two, that is TSSC and TCSC. Okay, firstly I will take the first one, that is GCSC, that is GTO thyristor controlled series capacitor. Okay, so I will take one diagram, so that will explain the elementary GTO thyristor controlled series capacitor. So actually this GCSC concept is proposed by Karady with others in 1992. So that is GCSC is discovered in the 1992. Okay, so that diagram is like this. Okay, so here we have one thyristor valve. So each thyristor consists of two thyristors. Okay, so this thyristor valve will act as a switch, and we have one capacitor and we have current. Okay, so here it consists of fixed capacitor, that is this one. Okay, fixed capacitor, and in parallel with the GTO thyristor valve, that is switch. Okay, this is the switch. This is also called as thyristor valve. Okay, so the thyristor, the capacitor is connected in parallel to the thyristor valve or switch. Okay, it has the capability to turn on and turn off upon the command. Okay, it has the capability to turn on and turn off the command. Okay, depending upon the command. And this compensator scheme is interesting in that it is the perfect combination of the well-established TCR. So in the shunt compensation, we discussed about the TCR concept. There is a thyristor controlled reactor, and this compensator scheme, that is the GCSC scheme, is interesting in that it is the perfect combination of the well-established TCR concept. That means it is having the unique capability of directly varying the capacitor voltage by delay angle control. Okay, that consists of the unique capability of directly varying the capacitor voltage by delay angle control. Okay, this is a diagrammatic representation of that one. And next, so apart from the theoretical interest, so this technique, as will be seen, has some operational merits. Okay, and it may be incorporated into some series compensator schemes in the future. And this concept, that is the TCS concept, is will be incorporated into some series compensator schemes in future, and particularly when larger GTO thyristors becomes available. Okay, when larger GTO thyristors becomes available, at that time we have incorporated this series compensator schemes in the future. And the objective of GCSC scheme is shown in the diagram, that is in the previous diagram, is to control the AC voltage, that is VC. Okay, is to control the AC voltage, that is VC, across the capacitor at a given line current I. Okay, so the objective of the GCSC scheme is to control the AC voltage, that is VC, across the capacitor at a given line current I. Okay, evidently, when the GTO valve, that is switch, is closed, the voltage across the capacitor is 0. The voltage across the capacitor is 0, that is VC is 0. And when the valve is open, it is maximum. That is, when the switch is open, it is maximum. The voltage across the voltage across the capacitor is maximum. Okay. So for controlling the capacitor voltage, the closing and opening of the valve is carried out in each half cycle in synchronism with the AC system frequency. So for controlling the capacitor voltage, that is VC, the closing and opening of the valve, that is switch, the closing and opening of the switch is carried out in each half cycle in synchronism with the AC system frequency. So the GTO valve is stipulated to close automatically whenever the capacitor voltage across 0. Okay. So the GTO valve, that is a switch, is stipulated to close automatically whenever the capacitor voltage across 0. So when the switch is closed, means the capacitor voltage is 0. That is VC is equal to 0. So when the switch is open, the capacitor voltage is maximum. So however, the turn off instant of the valve in each half cycle is controlled by a delay angle, that is gamma, that is in between 0 to pi by 2. Okay, with respect to the peak of the line current. With respect to the peak of the line current. So I will show one more diagram. There is a waveform diagram. So this one. Okay. So actually this diagram shows the positive half cycle, negative half cycle of the GCSC. Okay. So refer to the diagram. So in that one, the line current I and the capacitor voltage VC of gamma are shown at gamma is equal to 0, that is at valve open, there is a switch open condition, and at an arbitrary turn of delay angle gamma for a positive and negative half cycles. Okay, so if you see this diagram, you will understand. So I will take the diagram. So it is versus I versus T. There is a current versus time T. So that is the first waveform. The left diagram is for the positive half cycle, and the second diagram is for the negative half cycle. Okay, in that one we have 3 curves. Okay, 3 curves we have. One is for the VC, that is the voltage across the capacitor at gamma is equal to 0, and one more curve is there, that is for the VC of gamma. Okay, like that we have. In that one we have minus 1 by omega c sin delta. Okay, sin gamma, and we have the angles, that is gamma and zeta. So gamma and zeta we have. Okay, and on the right side we have the negative half cycle. At that time we have 1 by omega c sin gamma. In this one we have VC of gamma, and VC of gamma is equal to 0. Okay, like that we are taking. So refer to that one. In that one, the line current I and the capacitor voltage VC of gamma are shown at gamma is equal to 0. That means the switch open condition, and at an arbitrary turn of delay angle gamma for positive and negative half cycles. So when the switch is opened at the crest of the line current, that is gamma is equal to 0, the resultant capacitor voltage will be same as that obtained in steady state with a permanently open switch. Okay. Next, so when the opening of the valve is delayed by the angle gamma with respect to the crest of the line current, the capacitor voltage can be expressed with a defined line current, that is I of t is equal to I cos of omega t as follows, that is Vc of t is equal to, that is the opening of the valve, the voltage across the capacitor is Vc of t is equal to 1 by c integral gamma to omega t I of t dt. So that is equal to, we know already I of t is equal to I cos of omega is substituted here in the I of t place, and after integrating this one we have 1 by omega c sin of omega t minus sin gamma. So treat this equation as 6.7, and since the valve opens at 1 dash and stipulated to close at the first voltage 0. Okay, whenever the voltage is open, when after the first voltage is 0, is valid for the interval, that is omega t is in between gamma to pi minus gamma. Okay, omega t is between gamma to pi minus gamma, and for subsequent positive half cycle intervals, the same expression remains valid. And for subsequent negative half cycle intervals, the sign of the terms becomes opposite. So if you have the positive half cycle, that means positive term, and it will become opposite in the negative half cycle. That is minus. And comparison of 6.7 to 5.4, that is 5.4 is derived in the TCSC concept in the shunt compensation, that is the 5.4, that is IL of t is equal to 1 by L into integral alpha to omega to v of t dt, and we have at that time we have the equation IL of t is equal to v by omega L into sin of omega t minus sin alpha, and in the 6.7 we have Vc of t is equal to 1 by omega c into sin of omega t minus sin gamma. So these are the equations we have in the TCR and in the GCSC concept. So comparison of these two equations for the current of the TCR indicates that the two equations are formally identical and can be interrupted in the same manner. Okay. Next, in the 6.7 form, that is Vc of t is equal to 1 by omega c sin of omega t minus sin gamma. So in this one, the term 1 by omega c into sin gamma is simply a gamma dependent constant by which the sinusoidal voltage obtained at gamma is equal to 0 is offset and shifted down for positive and up for negative voltage half cycles. This will be illustrated in this diagram, that is positive and negative half cycles of the diagram. And since the GTO valve automatically turns on at the instant of voltage 0 crossing, okay, since the GTO valve, there is a switch automatically turns on at the instant of voltage 0 crossing, this process actually controls the non-conducting interval of the GTO valve. There is a blocking, okay, there is a blocking, and that is the turn-off delay angle gamma defines the prevailing blocking angle, that is zeta. So that is zeta is equal to pi minus 2 gamma. So you have the turn-off delay angle gamma is defined the prevailing blocking angle, that is zeta. So thus, as the turn-off delay angle gamma increases, the correspondingly increasing offset results in the reduction of blocking angle zeta of the valve and the consequent reduction of the capacitor voltage. So at the maximum delay of gamma is equal to pi by 2, the offset also reaches its maximum of 1 by omega c, at which both the blocking angle and the capacitor voltage becomes 0. That is the zeta is 0 and Vc is equal to 0. Okay. And it is evident that the magnitude of the capacitor voltage can be varied continuously by this method of turn-off delay angle control from maximum to 0, that is gamma is equal to 0 to gamma is equal to pi by 2, as illustrated in the figure. So I will show the diagram, this one. So here I am taking the current voltage waveform. So capacitor voltage, the voltage across the capacitor at delay angle gamma, and the capacitor voltage across the voltage across the capacitor is the fundamental at delay angle gamma. There is gamma is equal to 0 to gamma is equal to gamma 4. with respect to the time, that is omega t. So that is, it is evident that the magnitude of the capacitor voltage can be varied continuously by this method of turn-off delay angle control from maximum, that is gamma is equal to 0 to gamma is equal to pi by 0, as illustrated in the diagram. So where the capacitor voltage, that is Vc of gamma, together with its fundamental component, that is Vcf of gamma, are shown at various turn-off delay angles gamma. So this is a diagram representation of that one. So note, however, that the adjustment of the capacitor voltage is similar to the adjustment of the PCR current, is discrete and can take place only once in each half cycle. Okay, the adjustment of the capacitor voltage, that is Vc, similar to the adjustment of the PCR current, that is IL of t, is discrete and can take place only once in each half cycle. In comparison of the figure, that is 6.5, that is this one, with the 5.7, that is this one. Okay, so this one, see diagram. Okay, here also we are taking alpha is equal to 0 to alpha is equal to alpha 4. That is for the PCR, that is for the PCR. Okay, so at that time we are taking the delay angle alpha, and in the GCSC we are taking delay angle gamma. Okay, so comparison of these two diagrams shows that the wave shape obtained for the current of thyristor controlled reactor, that is TCR, is identical to that derived above for the voltage GTO thyristor controlled series capacitor, that is GCSC, and confirms the duality between the GCSC and TCR. So indeed, the duality between the TCR and the GCSC is quite evident. So the TCR is a switch in series with a capacitor, with a reactor in the TCR concept, and the GCSC is a switch in shunt with a capacitor in the GCSC concept. So the TCR is supplied from a voltage source, and the GCSC is supplied from a current source. That means in the TCR we are using the transmission bus voltage, and in the GCSC we are using transmission line current. Okay. Next, the TCR valve is stipulated to close at current 0 and the GCSC at voltage 0. So the TCR valve is closer to current 0 and GCSC at voltage 0. So the TCR is controlled by turn-on delay with respect to the crest of the applied voltage, which defines the conduction interval of the valve, and the GCSC is controlled by a turn-off delay with respect to the peak of the line current, which defines the blocking interval of the valve. So the TCR controls the current in a fixed inductor from a constant voltage source, thereby presenting a variable reactor admittance as a load to this source, and the GCSC controls the voltage developed by a constant current source across a fixed capacitor, thereby presenting a variable reactive impedance to this source. This is the difference between TCR and GCSC schemes. So the duality established above makes it possible to use the analytical results given in, that is the diagrams, and to extend the circuit structural and operational considerations applied to the TCR in the previous chapter, that is shunt compensation, to the GCSC and related series capacitor compensators. So thus, from the figure A, the amplitude VCAF of gamma of the fundamental capacitor voltage VCAF of gamma can be expressed as a function of the angle gamma, that is VCF of gamma is equal to 1 by omega c of 1 minus 2 by pi into gamma minus 1 by pi sine 2 gamma. So this is treated as equation number 6.8a. And next, so from that equation, so I is the amplitude of the line current and C is the capacitance of the GTO thyristor controlled capacitor, and omega is the angular frequency of the AC system. So omega is the angular frequency of the AC system, and the variation of the amplitude, that is VCF of gamma, normalized to the maximum voltage, that is VCF of gamma is equal to 1 by omega c, is shown plotted against the delay angle gamma in figure 6.6, that is this one. Okay. So on the basis of figure 6.6, the GCSC varying the fundamental capacitor voltage at a fixed line current, so could be considered as a variable capacitive impedance. So indeed, an effective capacitive impedance can be found for a given value of gamma or in other words, an effective capacitance impedance Xc as a function of gamma for the GCSC can be defined. So I will show the diagram, that is this one. So this is the diagram. It will give the fundamental component of the series capacitor voltage versus the turn of delay angle gamma. Okay, so on the right side we have the circuit representation for this operation. So in this one I am taking a thyristor valve which consists of the fixed capacitor, and the voltage across the capacitor is Vc of gamma, and we have the line current I, and we have the thyristor valve, that is switch. So by using this we are drawing the fundamental component of voltage across the capacitor at delay angle gamma. It will taken in per unit terms. So and gamma is taken in delay angle is taken in the degrees of 0 to 90 degrees, and the VCF of gamma, that is voltage across the fundamental voltage across the capacitor at delay angle, is taken per unit, that is 0 to 1 per unit. So we have the curves. We have three curves. So one curve is in between VCF of gamma at 1 per unit to 90 degrees, that is VCF of gamma, and we have 1 minus 2 pi by gamma and 1 minus 1 by pi sine 2 gamma. Like that we have the curve. Okay, and from the 6.8 equation A, this impedance can be written directly from that one, that is Xc of gamma, that is equal to 1 by omega c into 1 minus 2 by pi gamma minus 1 by pi sine 2 gamma, and this equation is treated as a 6.8b. So evidently the admittance Xc of gamma varies with gamma in the same manner as the fundamental capacitor voltage VCF of gamma, that is from the previous diagram. So in a practical application, the GCSC can be operated either to control the compensating voltage, that is VCF of gamma, or compensating reactance, that is Xc of gamma. Okay, so in the voltage compensation mode, the GCSC is to maintain the rated compensator voltage in phase of decreasing line current over a defined interval, that is I is lies between I minimum to I maximum, as illustrated in 6.7a1, that is this one. This is the diagram. Okay, in this one we have the VA characteristics. Okay, VA characteristics. Okay, so on the x-axis we have current values, and on the y-axis we have the capacitor voltage. So here we have minimum current and maximum current. Here the current is lies between minimum to maximum current, that is I minimum and I maximum, and we have the maximum capacitor voltage, that is VC maximum. So here the diagram is like this, and we have the cross lines. Okay, so in the voltage compensation mode, the GCSC is to maintain the rated compensating voltage in case of decreasing the line current over a defined interval, that is I minimum to I maximum, that is shown in this diagram. Okay, next, so in this compensation mode, that is in the A1 diagram mode, the capacitive reactance, that is Xc, is selected so as to produce the rated compensating voltage with I is equal to I minimum, that is VC maximum is equal to Xc I minimum. So as current I minimum is increased towards I maximum, the turn of delay angle gamma is increased to reduce the duration of the capacitor injection and thereby maintain the compensating voltage with increasing line current. So the loss as percent of the rated wear output versus line current characteristics of the GCSC operated in the voltage compensation mode is shown in the next diagram, that is 6.782. That is for the zero voltage injection, and for the maximum rated voltage injection, that is VCF of gamma, that is equal to VC maximum, and the VCF of gamma, that is equal to 0. So this is the diagram we are taking. So this is the graph between loss versus line current. Okay, so this is the diagrammatic representation of that explanation. So here we have VC maximum and the VCF of gamma is equal to 0. So here I am taking losses in the percentages of 0 to 0.5. Okay. Next, so in the impedance compensation mode, the GCSC is maintaining the maximum rated compensating reactance at any line current up to the rated maximum is illustrated in the figure this one. Okay. So in this compensation mode, the capacitive impedance is chosen so as to provide the maximum series compensation at rated current, that is Xc is equal to Vc maximum by I maximum, that the GCSC can vary in the, that is XA of gamma is vary between 0 to XC range by controlling the effective capacitor voltage, that is VCF of gamma, that is XA of gamma is equal to VCF of gamma by I. So the loss versus line current characteristic of the GCSC for this operating mode is shown in the figure, that is 6.7 B2 for zero compensating impedance and for maximum compensating impedance. So this is for the first explanation, that is 6.7 B1. So here we are taking the current versus voltage, that is VA characteristics, compensating voltage versus line current, and characteristics of the GCSC with operating voltage control and reactances, that is B1, and E1 and B1 for this explanation. So here we have maximum current and maximum capacitor voltage, and we have the capacitor reactance. Okay, this is for the B1 diagram, and this is for the B2 diagram. So in this one, we are taking loss versus current characteristics, line current characteristics. So here XA of gamma is equal to 0. Okay, next. So the impedance and the voltage compensating mode, the impedance and voltage compensating mode are of course interchangeable by control action within the rating limitation of the series capacitor controlled. So it should be appreciated that to realize the theoretically defined operating VA area shown in the previous ones, that is in the 6.7A1 and 6.7B1, the power components in the GCSC must have the corresponding voltage and current ratings. So in practical applications, series compensators are often required to have increased short duration ratings, and they can be exposed to significantly higher than the normal or short-term rated maximum line current during the line faults and other major disturbances. Okay. So such fault currents would generally be too high for the GTO valve to conduct. Okay, such fault currents would generally be too high for the GTO valve to conduct. So however, if the valve is turned off, that is the switch is turned off as a protection measure, then the voltage across the GCSC capacitor could become excessive both for capacitor and the parallel connected valve. Okay, thus in practice, it would usually be necessary to protect the GCSC externally, either by external voltage, that is MOV arrestor, or the voltage limiting device, or by an appropriate bypass switch arrangement. So which would ensure that the defined voltage and current ratings of this GCSC would not be exceeded under any operating condition. So it should be noted that this protection requirement is not unique to GCSC. So indeed, practically all series connected compensators, including the conventional uncontrolled series capacitor, require a similar protection arrangement. Okay, so the turn-off delay angle control of the GCSC, just like the turn-on delay angle control of TCR, generates harmonics, that is from the Chandy compensation. So these are combined to generate the harmonics. First now we discussed about the main operation of the GCSC scheme, and now we discuss about the harmonics. So for identical positive and negative voltage half cycles, only odd harmonics are generated. Okay, and the amplitudes of these are a function of angle gamma, and for that from the equation, that is 5.6, can be expressed in the following form, that is VCN of gamma is equal to 1 by omega c into 4 by pi into sin gamma cos of n gamma minus n cos gamma into sin of n gamma by n into n square minus 1. So here n is equal to 2k plus 1. So here k is equal to 1, 2, 3 and so on. Okay. So the amplitude variation of the harmonics expressed as a percentage of the maximum fundamental capacitor voltage is shown plotted against gamma, that will show in the diagram. So this one. Okay. So the elimination of the triple N and the harmonics families in the capacitor voltage by the usual methods of three-phase operation and multi-pulse circuit structures are probably not practical for the GCSC, because those approaches would usually require an insertion transformer, and the GCSC, like other series compensating capacitors, would normally be inserted directly without any magnetic coupling in series with the series with the sufficient insulations. Okay. So this is the diagrammatic representation of the explanation. So here I am taking Vn, that is the voltage, and turn-off delay angle gamma. So here gamma is taken between 0 degrees to 90 degrees, and we have different curves. That is for the V7, V9, V11, and V13. All are for the odd. Okay, this is the circuit representation. So here we are taking the thyristor valve in parallel with the capacitor. Here we have line current I, then the thyristor valve, that is switch, then the voltage across the capacitor, that is Vc of gamma, and we have the waveforms like this I versus Vd. Okay, so this is the explanation for that one. And next, so the GCSC, like other series compensating capacitors, would normally be inserted directly without any magnetic coupling, so in series with the line. So if operated on a high voltage platform of sufficient insulation level, so the effect of these harmonics may be relatively small, particularly if the transmission line impedance at the harmonic frequency is considered is relatively large. Okay, next, however, if necessary, the magnitudes of the harmonics generated by GCSC can be attenuated effectively by the complementary application of the method of sequential control introduced for the reduction of PCR generated harmonics in the previous chapter. Okay. So recall that this method stipulated the use of m greater than or equal to 2 in parallel connected TCRs, each with 1 by m of the total rating required. Okay, so the reactors are sequentially controlled, that is only one of the n reactors is delay angle control, that is for the TCR case, not for the GCSC. Okay, so and each of the remaining m-1 reactors is either fully on or fully off. So the method of sequential control eminently suits for the GCSC also. So it follows from its duality with the TCR that it requires the use of m greater than or equal to 2 series connected GCSCs, each with 1 by m of the total rating required, that is the voltage, total voltage. So as mentioned in the figure, that is in this figure, okay, all but one of n capacitors are sequentially controlled to be inserted by or bypassed. Okay, so here I am taking n capacitor, that is Vc total is equal to Vc1 plus Vc2 plus Vc3 plus Vc4, like that. So here I am taking 4 combinations. Okay, 4 GCSC schemes we are taking, and on the right side we have the waveforms of these four GCSC schemes. So first waveform is for the capacitor voltage, that is the fixed capacitor, and next we have Vc1, Vc2, Vc3 and Vc4, and lastly we have the total capacitor voltage. Okay, so like that we have here the waveforms is gone between Vc versus time, that is t. So waveforms illustrating the method of controlling 4 series connected GCSC bands, that is Vc1, Vc2, Vc3 and Vc4 sequentially to achieve harmonic reduction. Okay. Next, the single capacitor turn-off delay angle. Okay, the single capacitor is turn-off delay angle controlled to facilitate continuous voltage control for the whole GCSC over the total operating range. So with this arrangement, that is previous arrangement, the amplitude of each generated harmonic is evidently reduced by a factor of m in relation to the maximum total fundamental compensating voltage. So note that in contrast to the TCR arrangement, where for economic reasons only a relatively small number of parallel branches would be applied, there is no significant economic disadvantage and maybe technical preference to break a single high voltage valve into 4 or more series connected modules to realize a practical GCSC. So this explanation from the previous track. There is the 4 GCSC schemes. So the losses of the sequentially controlled GCSC are inversely proportional to the wear output, that is I rated square into x into GCSC, x suffix GCSC. So the losses are maximum when all the capacitors of the sequentially controlled GCSCs are bypassed. So they are negligible when all the capacitors are fully inserted, that is all GPOs are off. Next, in view of the on and off operation of the all but one of the GCSC modules, the question actually arises, that is, why not replace the GTO valves in the M-1 module? So here we are replacing M-2 module. So here they are asking, why not replace the GTO valves in M-1 modules with less expensive conventional thyristor modules? So the answer is that with conventional thyristor valves, the operation of the total valve would become difficult. Okay. With conventional thyristor valves of operation of the total valve would become difficult. So in other words, the conventional thyristor valve cannot imitate GTO valve operation even for full conduction capacitor switching. So refer to the diagram of the 6.5, that is B, that is in the negative and positive half cycles. Consider the full capacitor insertion producing the voltage valve wave, that is Vc of gamma is equal to 0. Okay. So note that in order to obtain this half cycle wave, the GTO valve must turn on and off when the capacitor voltage is 0, at which instant the line current is at its peak. Okay, the conventional thyristor valve could be turned on at the required instant of voltage 0, but it would only turn off at a current 0, and which occurs either a quarter cycle before a quarter cycle after the voltage 0, where the proper turn off should take place. Okay, so and in the next section I will discuss when the conventional thyristor valve turns off at a current 0, it produces a full DC offset for the capacitor voltage, doubling the maximum voltage stress on the valve and the time delay after which the capacitor could be again be bypassed. So in the next section I will discuss these things, and also the remaining two variable impedance type series compensators also I will discuss in the next class. Okay, thank you for watching this video.